Hello, everybody. It's Professor Steve Rehse. So very happy to be with you again, participating in another one of our fun and fantastic DoD K-12 Open STEM topic Zoom learning session. It has been a long time since we've been able to get together and talk about the topics in science, technology, engineering, and math that fascinate us so much. And I am just thrilled to be joining you all again after a brief hiatus. We are looking forward to a fantastic year of new talks that are going to delve deep into the mysteries of the universe, and I hope you are excited about that and ready to join us on that journey. So, welcome very, very much. Great to be back. So, we are here today. This is September of 2024. We're having our Waatebagaa-giizis, which is, I apologize for the pronunciation. I did the best I could. That's Ojibwe, Septiembre, Spanish, September, English, DoD STEM K-12 Zoom learning session version. So welcome to September. I would call this the autumn edition of our talks. So I have a very interesting topic for you all today, a topic that's near and dear to my heart. I am a physicist. I'm a professor of physics. I'm the head of the Department of Physics at the University of Windsor, and specifically, I am an atomic physicist, and that means that I study atoms. My whole career has been devoted to thinking about atoms. So today I'm going to talk to you about atoms, and I think we're going to learn a little something, and we might even have a little bit of a laugh. So let's just see how it goes. I'm going to share my screen. I've got a presentation I put together for everybody. I hope you're going to enjoy it. Let's see how that looks. There it is. So you can see from the topic that I'm kind of starting us off with a little bit of a teaser, which is why you can't trust atoms. By the end of this talk, you are now going to know why you can't trust atoms. But you got to bear with me for about 15 minutes to get the answer to that question. So I hope you're willing to come along for the ride. As always, I'd like to start with our land acknowledgement statement from the University of Windsor. I'm showing an aerial photograph. This is Windsor, Ontario, Canada, right here. It is one of the southernmost cities in all of mainland Canada. And as you see, we are situated directly south of the great metropolitan city of Detroit, Michigan. And as you know, these DoD STEM talks are offered in collaboration with our partners in the United States and our partners here in Windsor, Ontario, Canada. Very happy to be joining you all today, whether you're watching from Canada or the United States. The University of Windsor, which sits right about here on this map, sits on the traditional territory of the Three Fires Confederacy of the First Nations, which includes the Ojibwe, the Ottawa, and the Potawatomi. We respect the long-standing relationships with First Nations people in this place, in the 100-mile Windsor-Essex Peninsula, which is here, and the Straits, Le Detroit of Detroit. And I love this aerial photograph, which is actually showing you the Straits, Le Detroit of Detroit, this thin sliver of water that separates our two great countries. So, what is an atom? That's what I want to get into today. What is an atom? Well, an atom is basically the smallest unit of an element that retains all the properties of that element. It's the element that can't be divided up any more finely. What are elements? These are the things that you might be familiar with from something called the periodic table, but the elements make up all the materials around us. They could be hard materials like carbon or silicon, germanium, things like tin, antimony. They can be gases like oxygen that we breathe and nitrogen that we breathe, argon and chlorine, which is very dangerous, and xenon, which is lit up in some types of light bulbs to make them very bright. It could be liquids like iodine. All of these elements are the different materials that compose everything we know of in the universe and are listed on the periodic table if you're starting to learn a little bit about chemistry. So the atoms are the bits of the elements that cannot be divided up any smaller and still retain the property of that element. What we know is that everything is made up of atoms. So you and the rest of the universe are all made up of these small items that we call atoms. And that's what I'm going to just give you a flavor of today, what exactly an atom is. So let's take another example of an element. This is a brick of gold. Beautiful, shiny, metallic gold. Gold has a chemical symbol that's AU. Why is it not GO? Well, you're going to learn as you start to study science that sometimes scientists use different letters for things. We like to talk in different languages sometimes, and you're actually going to see an example coming up in just a little bit of a different language that has incorporated itself into our science. But I believe that you're all going to be familiar with this object here. You've probably seen it, hopefully, in TVs or movies, a solid brick of really heavy gold. It's really, really valuable right now. So if you had that a brick of gold, let's assume this is pure solid gold, this would be worth a lot of money. But maybe you didn't want that brick all for yourself. Maybe you wanted to break it up into chunks and give it to all your friends so they could have money too. Well, how small can you break that brick up into? You might take a big hammer to it, smash it all apart. Then you're going to wind up with just nuggets of gold. It's not a brick anymore, but these are all still pure gold nuggets. There's many areas in the western United States where people can still pan for gold. This is actually what led to the gold rush in the western parts of the United States and up in Canada at the time that this gold was just lying around at the bottom of rivers coming out of the mountains. So all you had to do was take a pan. That's why they call it panning for gold. And you can pick up some of these nuggets and make your wealth that way. So it's a small chunk of gold. It's much smaller than this, but it's still gold. What if you wanted to take that nugget and you wanted to break that up even finer? You got a really good knife or something and you want to just chop it up as small as you can. Well, you might reduce that gold nugget to gold powder. This is still gold. You can see it's still kind of yellowy and metallic there, and here. This is a powder. It would be like sand. I think you've all seen sand. So just imagine that sand is pure gold. This is like 100% basically pure gold. It still has all the properties of gold, but it's much, much more finely divided. Is there any end to how finely divided you can make that gold and have it still be gold? If I wanted to take something and keep chopping it in half and in half and in half and in half, there is. An atom of gold is the last thing. An atom of gold is the smallest object that is still gold and retains all of those properties. It cannot be subdivided anymore and still be gold. So there is a limit. You can't just forever keep making something smaller and smaller and smaller. Eventually you get to an atom, and that is the fundamental building block of matter, of all the things that we see around us. So I want to talk about what this atom is today, what we know about it, and kind of what a mysterious thing that it actually is. I just love these animations of atoms. We're going to talk about what all these things are in just a little bit. What I find interesting is that every atom of an element, say gold, let's keep using that example, every atom of gold everywhere in the universe is absolutely perfect and identical. This is the way nature works. There's not little variations between them. There may be people in your family where there's variations between you. The atoms are identical. Every place in the universe, an atom of gold on the other edge of our universe is going to be identical and perfect and completely indistinguishable from an atom of gold here on Earth. Everywhere in the universe, for all the history of time, it's perfect and unchanging. These atoms don't degrade, they don't age, they don't wear, they don't weather away like rocks. Even the Grand Canyon is very old, but those rocks weather away with the water. The atoms do not weather away. There's no wear and tear, there's no friction. They're indivisible, they are perfect, they're essentially eternal, many of them. It's an amazing thing, and that's why it's the building blocks of all the matter that you see around us. So these atoms everywhere in the universe are identical to each other, but the atoms of every element are different from the atoms of every other element. So every gold atom in the universe is the same, but they're all different from every atom of silver in the universe. And those are different from every atom of aluminum in the universe, and et cetera, et cetera. So this variation is what gives our universe the structure that it has. So how do we know about these atoms, or how long have we known about them? You note that I haven't shown you any pictures of atoms yet. I keep showing these animations of things swirling around and moving and rotating. That's because an atom is so small, and I'm going to tell you how small in a second. It's so small I can't show you a picture. We don't have pictures of these things at all. We have to kind of conceptualize what we think it might be if we could actually see something that small, but we just can't. And so you might think something that's small, we've only discovered it fairly recently. It's actually not true. The idea and the word for atom goes back to ancient Greece. And in this case, ancient Greece about 2,400 years ago. So if you could go back in time that long, there was a brilliant Greek philosopher named Democritus. Democritus had this idea, and he proposed a Greek word for this idea. So he proposed the Greek word atomos, and here are some Greek letters. So very common in physics to use Greek letters in our communications. And this is the word atomos written out in Greek. And this means uncuttable or indivisible, if you could translate it into English. It's this idea that it's the small thing, that it is uncuttable. It's not that there's nothing sharp enough to cut it. It's just not possible to be divided. It is the quintessential bit of matter. And he then proposed the idea that all matter was eventually, if you could keep making it smaller and smaller and smaller, reducible to these little discrete small particles that he called atomos. And we now know that that actually is true. That's what composes everything, including you, these small individual atoms. So if they compose everything and you're composed of them, they must be pretty small, right? So how small is small? Well, I have a hard time explaining how small that is. So let me give you an example. Here's your human body. If you could go up and count up all the atoms that exist in your human body, there are about 6.5 octillion atoms in the human body. So you've learned a new word today, octillion. How many is that? Well, that's 6,500,000,000,000,000,000,000,000,000,000,000,000,000 atoms. That's a lot of atoms. So you might use like billions and trillions and quadrillions. This octillion is way more than that. So 6.5 octillion atoms in your body, and you're not that big. So they must be really, really, really small to fit that many atoms all inside your body. And yeah, they are really, really small. So let's take a look at how small they actually are. This is just kind of a neat diagram that shows the length scale of biology. I'm just using this because you're probably familiar with how big you are, and I want to relate how big you are to how big an atom is. So on this particular chart, this length scale, you're on one end and the atom's on the other. You're a human being. You're roughly a meter in size, let's say. Of course, heights vary and everything, but around about a meter. And at the very end, with some numbers that I can't even really explain to you, we call it zero point 0.1 nanometers, is the atom, much, much smaller. And in between are these things that you might be familiar with: the width of a human hair, a fruit fly, the human red blood cells, viruses that can make you sick, and DNA and proteins. I'm just going to give you a couple examples here so you can scale an atom relative to yourself using this arrow here and some other arrows that are going to appear. So here's you at about a meter. I hope most of you know frogs. You've probably seen frogs jumping around in lakes or ponds. They're small little amphibians. And when a frog is born, it comes from a frog egg, which is even much, much, much smaller than the frog itself. That frog egg is really tiny. How tiny is it? It's about 1,000 times smaller than you. So these small little frog eggs, which are about a millimeter, roughly 1,000 times smaller than you. And that's pretty small, but it's still gigantic compared to an atom. So if we want to go even smaller, I could go 1,000,000 times smaller. If the frog egg was 10,000 times smaller, what if I think about something that's 1,000,000 times smaller? And that would be the bacteria. Sometimes you might get a bacterial infection, and then you have to take something like antibiotics to make yourself healthy again. But when you have a bacterial infection, you actually can't see the bacteria. They're so small. They're 1,000,000 times smaller than you. They're the size of something that we call a micron, really, really small, almost invisible, even with a good microscope. They're right on the edge of our conventional microscopes. You can barely, barely see them. But guess what? The bacteria is still huge compared to an atom. To get to the atom, you have to go 10,000 times smaller than the bacteria, which is already 1,000,000 times smaller than you are. So 10,000 times smaller than the bacteria is this atom. It's one of the smallest things that we can kind of define and know about in our universe. We're getting to the smallest things that there even really are. That's why I find them so fascinating to study. So they're so small. Are they simple? Are they boring? They're not simple or boring. They have some really neat structure that I want to talk about. They're relatively simple because an atom is really composed of two different things. It's going to be a nucleus at the center and some electrons that kind of are swirling and moving all around it. So let's talk about what that means. At the very center of the atom is this thing we call the nucleus. So I hope it shows up on the screen. You can see kind of a gray cloud. This is the way we really are envisioning an atom. It's intentionally faint. I know it might be hard to see the screen, but it's like that for a reason. It's a wispy kind of thing. But at the center of the atom is this nucleus. And we use that word a lot in science, right? Your cell has a nucleus, the core bit. If you have a really good football team this year, there might be a few individuals, maybe the quarterback and the running back, and we say they form the nucleus of the team, right? The heart, the small, really important bit. And that's what the nucleus is. It's the small, really important bit at the center. And guess what? It's small. It is 100,000 times smaller than the atom. I just got done trying to tell you guys how small the atom actually is. Well, imagine this nucleus at the center is 100,000 times smaller than that. It's really small. And there's going to be something even smaller yet, but now we're getting incredibly small. But the interesting thing is it's small, but it has all the mass. So all the mass of the atom, the thing that gives it weight, now it's small, but it still has weight and mass, just like you do. All of that mass, almost all of it, is concentrated in the nucleus. So it's empty space, but all the weight and mass is actually in the small little grain of sand kind of thing at the center of it. And the nucleus is composed of two different types of objects that we call nucleons, things that exist in the nucleus. And they're composed of protons that I'm showing kind of as red balls here, and neutrons, which I'm showing as black balls here. They're not really balls, but this idea of thinking of the protons and neutrons stuck together in a nucleus is not a bad way to think about it when you're trying to understand it. And so that's the nucleus. And then you have these electrons that are even smaller than the nucleus. All right. So what we really envision an atom being is this heavy nucleus at the center, and it's surrounded by a cloud of electrons, a whirring cloud where these electrons are in constant, unbelievably fast motion about the nucleus. So they're extremely tiny, these electrons. They're at least 1,000 times smaller than the nucleus. So I said the atom is super small. And then I said, hey, the nucleus is about 100,000 times smaller than that. Then I said the electrons have a diameter that's about 1,000 times smaller than the nucleus. So those are essentially the smallest things that really have matter and exist in the universe, these teeny tiny electrons that are whirling around at unbelievably fast speeds around the nucleus. And this interaction of this heavy little grain of sand with the mass and this whirling cloud of super light electrons gives that thing that we call an atom all of its properties. And it's a pretty strange place to try to investigate, but it's really, really fascinating. But what I'm trying to tell you is that atom is mostly empty space, the small little grain of sand type thing, and this huge whirling cloud around it. But it's empty in between. That's all that there is. There's nothing there. It's empty space. This atom, which comprises you and everything you know, is mostly empty space. There's just nothing there. And that is kind of a mind-blowing idea. How empty is it? Well, here's a schematic of an atom. I'm just trying to give you an analogy so you can roughly understand how empty it is. If an atom, if we were able to blow up an atom to the size of a football field, so I think you've all seen, at least on TV, maybe even stood on an American or Canadian Football League football field, you know how big that roughly is. So if an atom were a total size of the football field, the nucleus would just be a small marble sitting at the 50-yard line. A marble is just a little round thing about the size of the end of your pinky. Place that on the 50-yard line, and then the atom is all the way to the other end zone. So you can tell that it's a giant thing where there's nothing there because most of the nucleus is the small little thing at the middle, really, really empty. And so you might think, wow, that's kind of a strange situation to be in. But it's not that strange. Let's talk about empty space for just 1 second. Our solar system is also mostly empty space. Everybody knows a little bit about our solar system. There's the sun, and then a long ways away, for example, is the Earth, and then a long ways away are these other planets. There's nothing in between that. That's also mostly empty space. So I'll give you another just example just because it's so big. We have to do this because I can't just tell you the numbers. It won't mean anything to you. You always, when you're doing science, you have to try to understand it with scales and numbers and sizes that you can understand. So let's just pretend that the sun is not this gigantic orb. Just imagine the sun is something like a foot wide. Could be a small soccer ball, about that big. You've all kicked those around, so you know how big that is. That's the sun. If that's the sun, how far away would the Earth be? Well, the Earth would be a small speck 215 feet away and nothing in between. That's empty. And one of the farthermost planets that we have, Pluto, which is not really a planet anymore, it kind of got voted out, planetoid, but on this graph, it's still listed there. So let's just include it. It's one of the outermost objects that we kind of know about. Pluto would be a planet from this 1 foot big soccer ball. It would be an object 1.6 miles away with nothing in between. That's what we mean about the emptiness of space. There's really not a lot there with these big, huge, vast, empty tracks in between. And so is the atom more empty or less empty than that? Let's take a look. Well, if I can use the exact same kind of analogy where not the sun being a foot wide, but say the nucleus of a gold atom is about a foot wide, just do something like that, then where would the electron be, this whirling cloud of electrons that's going around the nucleus? If the nucleus was a foot wide, one of those electrons would be roughly 3.3 miles away, a little over 2 times further away than Pluto is. So the atom is even more empty than our solar system, which is a pretty empty place. And so that means most of our universe is actually made up of very empty space, but yet it's comprised of the interactions between the particles moving around in this empty space. This is our current understanding of the state of existence. It's kind of a very neat thing to study and to try to get your head around. But this is the way things actually are. So now we know what an atom is comprised of. We know what its size is. What does an atom do to make up you? It's not very common, actually, to encounter these atoms in their indistinguishable, indivisible form. Like if you look at my hand, there's no loose atoms here. I can't grab things and pull off atoms because the atoms don't exist in the loose form. Atoms really like to come together. They like to join into different combinations. And when they do that, they join together to form structures that we call molecules. And maybe you've heard that word before. A molecule is just a couple atoms, maybe a lot of atoms, that have come together and bonded together in a semi-permanent manner. So this is, for example, water, a simple molecule. It's simple because it's only 3 atoms. It's 2 atoms of hydrogen, which I'm showing here in white, and 1 atom of oxygen, which I've shown here in red. So 3 atoms, that's a pretty simple molecule. A molecule is a stable structure. These 3 atoms have joined together temporarily, but it doesn't take a whole lot of energy to go in there and tear that molecule apart. That you can do without too much problem. But remember, the atom's indivisible. It cannot be reached into and pulled apart. Not easily, not at all. So the molecule is a temporary combination of these things. Atoms and molecules don't have to be simple like water. Atoms can come together to form much more complicated molecules. So here's a molecular structure or something much more complicated. So you can see it looks like about 15, 20 atoms in this molecule, and this molecule will have some pretty interesting chemical properties because it's got a lot of interesting atoms in it. And this is by far not the biggest, most complicated molecule that atoms can form. Here's a molecule that I bet you all have heard of. This is a super complicated molecule. As a matter of fact, we call it a macromolecule, and it's DNA, right? And I bet you've all heard about DNA from watching crime shows or true detective shows and movies where they're trying to solve a crime, and they're doing DNA, and DNA is inside of each one of our cells. And it's this very, very long, complicated molecule. But guess what? Still made up of atoms. So I'm showing a double helix twisted strand of DNA here, but each of these colored dots, these orbs, these are individual atoms that are making up this molecule. So there are many, many, many atoms that make up a very complicated DNA strand, but it's still just atoms that have come together in temporary combinations that we call molecules. And so now once you see that these atoms love to join together and they can join together in infinitely complex numbers of ways, you see how structure such as you begins to arise from the simplicity and beauty of the atom. It looks something like this. This atom is this perfect, beautiful, indivisible thing, and it gets together to form molecules, simple molecules, and you can understand that joining together to form these structures. The molecules can get together to form much larger structures we call macromolecules, like the DNA we were just talking about. The macromolecules then organize together and they can form things called organelles. And the organelles can get together and form things that we call cells. Now we're getting up to things that you can almost see with a microscope. You can start to see cells of your skin, for example. The cells all knit together to form structures called tissues. And tissue you can certainly see. So somewhere in between the cell and the tissue is where it goes from kind of being not visible to your eyes to visible with your eyes. And now you have tissues like the skin. Different tissues form together to form organs, like your stomach right here. And that's certainly a visible thing. And then the organs get together to form things called organ systems. And then your organ systems comprise you. So at the end of this line, the organizational levels of the body is you on one end, and at the very, very other end of that complicated chain of structure is the individual atom. It is the building block. There is nothing smaller than that that's joining together. The atom is this indivisible building block that leads all the way up the chain to you. And then, of course, even to bigger things like Jupiter and the sun and things like that, all atoms. So that's how the atoms are comprising what make you up. So basically, I had to finish now. That's the story of the atom. It's a complicated place. It's can be a simple idea, this nucleus with this whirling electron cloud, but it gives rise to almost unimaginable complexity in the different combinations that can be formed from these things. And it's a really, really interesting thing to study. And I've had a fantastic career as an atomic physicist thinking about these types of atoms. So now that we've heard the story of the atom, I thought I would just end up with a joke here. So I hope you appreciate this joke. So this joke comes to me courtesy of the internet. So thank you very much for our internet contributor. This is Jesse Bahanan. And the joke is, why can't you trust atoms? Hmm, why is that? Why can't you trust atoms? They make up everything. I didn't say it was going to be a great joke. It is certainly a joke. I hope you laughed. I laughed a little bit when I heard it the first time. I think that's a funny joke. So I hope you did too. That's all I have for you guys today. I hope you've learned something about atoms. I hope you learned a new word like octillion. I hope you laughed a little bit at that joke, and maybe you can go tell your parents. They might laugh a little bit too. So we've actually learned a few things and had a good outcome of the time that we've spent together. I really appreciate you all kind of spending some time with me watching this video. I hope you'll join us again in the future. There's going to be more of these DoD K-12 seminars coming up. So keep checking back on the channel, watch them whenever you can, and just keep on learning. There's no reason to stop. You want to learn more about atoms? You can learn more about atoms. So I hope you have a great rest of your day. Thank you so much. Bye-bye.